In 1556, the Mughal Emperor Humayun tragically fell to his death while hurrying from his library to the prayer room. His wife Bega Begum commissioned this magnificent tomb over 4.5 centuries ago, taking the exquisite reflection of mausoleum in the garden's serene pool. One wonders if this grand door is as ancient as the tomb itself. Arriving early in the morning, I contemplate my strength as I attempt to open it. Celebrate with me, I have conquered the largest door of my life. Now, as I step into the main chamber and pass the cenotaph, I find myself drawn to the intricate jali work that captivates my interest. This is one of the interesting tiles in the cenotaph area of the tomb. It is facing, you can see it's facing east, and we have the sunrise from the eastern wall, and the light is coming in. This beautiful tile, look at this beautiful tile, and just look at the different tiles which have been used in it. There are squares, there are these, I will call it kites, then there is this flat bottom boat. Boats are also of two kinds, so just next to the flat bottom boat, if you say this, there is a curved bottom boat. Then there is hexagon, and there is hexagonal stars. A number of different shapes thrown in to form this tile. And I think this is one of the interesting tiles where you have hexagons as well, hexagonal shapes, hexagonal stars, and hexagons as well as square thrown into the same tile. Now, if you look at the symmetry of this tile, if you carefully look at that, here there is a piece broken. So there is, if you look at this, then you can see that the squares actually have nice fourfold symmetry. You can see this is square, so this kite turns into this kite, turns into this kite, and turns into this kite by 90 degrees. Each turn is 90 degrees. So, and as you go further, so for example, this boat, then a 90 degree turn boat, another 90 degree turn boat, and another 90 degree turn boat. So the whole space around the center of the square has this fourfold symmetry. So the pattern has the fourfold symmetry around the centers of the square. So this obviously is a fourfold pattern, and we know that fourfold patterns are only of three kinds. Either they don't have just fourfold but no mirrors, or they have fourfold with mirrors passing through the fourfold, or they have fourfold and mirrors, but mirrors do not pass through the fourfold. So first of all, let's check whether there is any mirror passing through the fourfold. Obviously no, because you can see this kite and this kite damages the mirror symmetry, which may expect parallel to the edges of the square. So there is no mirrors passing through the fourfold center itself. But are there any mirrors at all in this pattern? Yes, you can see this, the center of the hexagonal star, and this vertical line actually is a mirror of the whole pattern. And similarly, the horizontal line is also mirror of the whole pattern. So, in conclusion, we have fourfold symmetry, we have mirror symmetry, but the mirrors do not pass through the fourfold. This much information is sufficient for us to conclude that this is a pattern P4GM, one of the 17 plane groups, P4GM. So it has fourfold, it has mirrors, but mirrors do not pass through fourfold, and G stands for glide. So there are supposed to be glide planes also in this pattern. So let's try to look at where are the glides. So we know that for P4GM, the glides actually pass through the lines joining the centers of the fourfold. So this line will be a glide line, and if you think about the surroundings of this square, so for example, let's look at this flat bottom board. So this board, and then we come here, half translation, there is no such board, and then a full translation, there is a parallel board here. So this from board to board, I have the full translation, but if I go to half translation from here, then I do have a board, but in a different orientation. And I will get that orientation if I reflect this board in the horizontal line here. So when I come to this location and I reflect, I will get this board. This board will come here in this orientation, and reflection will turn into that orientation. Now this is a beautiful window tile, and we have looked at it before, hexagon and hexagonal star. But let's look at a little bit actually more challenging tile, which is there here on the floor, and one does not pay attention to it because it is on the floor and has weather is not in the very pristine condition. It's actually an amazing tile. It's really challenged me a lot, because you can see there is a big star here, and if I count, let me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 12 pointed star, and there is a smaller star. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 9 pointed star. So a combination of 12 pointed star and 9 pointed star, and these black dumbbells and these kites, and also pentagons. We know regular pentagons cannot fit into a two-dimensional tiling, and it's quite clear that these are not regular pentagons but a slightly distorted pentagons. But whoever made it must be a real genius and has thrown all these shapes to make a nice periodic pattern. When I first looked at it, I could see that there is a mirror in this direction. You can see there is a mirror in this direction. So there is a, let me call this a horizontal direction. So there is a horizontal mirror, and you can see that there is also a vertical mirror. So initially, two mirrors and their intersection point twofold gave me this feeling that this is an MM2 kind of pattern, probably. But then, to my surprise, I realized that actually there are not only two mirrors at 90 degree here on this 12 pointed star, but actually mirrors are at 30 degree. So here, then a mirror at 30 degree, mirror at 60 degree, and then mirror at 90 degree. So all these are mirrors. For example, let me trace this. If I start with here as my 0, so this is 30 degree mirror. You can see I am working on the 30 degree mirror line and this exact mirror. Once we see that there is mirror in the pattern at 30 degree, that obviously indicates that this is actually a 6-fold axis and not a 2-fold axis. So the local symmetry here, the side symmetry here is 6 mm and not 2 mm. So once it is 6 mm, it's easy to now try to look for a unit cell and translational periodicity at 120 degree. So I can take from this 12 pointed star to this 12 pointed star, which is half of it, but you can imagine the complete one here with the center, and then I go at 20 degree here, I find this. So this becomes my unit cell boundary. This unit cell boundary, you can see that. So this becomes my unit cell of 6 mm, and you know that in the unit cell of 6 mm, the center of the unit cell is actually a 2 mm point, which is this dumbbell. Also between the edges, also you have these 2 mm. So all these black dumbbells, I'm calling them dumbbells, are actually centers of 2-4. You should also know that in P6 mm symmetry in the tile, you should always have a 3-fold symmetry. So within the unit cell, there should be 3-fold centers, and those 3-fold centers have nicely been exploited by whoever was the genius designed this tile to use a nonagon, 9-pointed star there. So 9-pointed star fits in with the 3-fold symmetry and sits there. And you can see there is a 3-fold symmetry, particularly if you focus on these black dumbbells. So there are 3 of them at 120 degree. Everything else also surrounding here has a 3-fold symmetry. So a nice, beautiful P6 mm symmetry, but very, very challenging to identify. At least it was, for me, a very challenging pattern. We have this nice tile just next to the center tower. And if we now look at this tile, a lot of interesting shapes have been thrown. There is this black 4-pointed star. There is this white 8-pointed star. And then we have these odd shaped hexagons for us. And we have these black kites, which are these. So this is forming a beautiful tile. If you look carefully, these 4-pointed stars are actually the 4 mm symmetry points. So we have our unit cell. You can focus here. These are the 4-pointed star, 4 mm, 4-fold symmetry. And in the center of the unit cell, you have the octagonal star. So that is another 4-fold. So you always know that in 4 mm symmetry, the corners and the center both are 4 mm, but they have different kinds of points. They are not in the same orbit, they are in different orbits. So you have 4 mm here, you have 4 mm here, and it's a nice 4 mm symmetry. Between the 2-4-fold, at the edges you will have the 2-fold, where you can see these are the 2-fold points. So we have this nice 4 mm symmetry just next to the center here. Look at this beautiful jali. Let's look at the shapes. We have this nice beautiful octagon. Then we have these dumbbell shapes, and we have these shapes which let's call the hut shape or the house shape. So these 3 shapes have been arranged nicely in this 2-dimensional periodic pattern. So let's begin with the octagon. Octagon on its own has 8-fold symmetry, but then 8-fold symmetry will not fit in a periodic 2-dimensional pattern. So that 8-fold must have been broken down either to 4-fold or 2-fold. In this case, let's look at the surroundings. We have these dumbbells, and dumbbell seems to be rotating by 90 degrees. So it appears, the immediate surrounding appears to have the 4-fold. But then when we further look at these little houses, and I try to rotate this house by 90 degrees, so that is not matching, because the tip of the ceiling of the house actually is not rotated by 90 degrees, but rather it seems to be reflected along this line. So this cannot be actually 4-fold also, so maybe it's 2-fold, and as I told you that this is a mirror line. So if it's a 4-fold, then there should be 4 mirrors, vertical, horizontal, and also at 45 degrees. But you can see that hut breaks this 45 degree mirror. So 45 degree mirror is not there. That also indicates that this is not 4-fold but only 2-fold, because we have a vertical mirror and horizontal mirror. So octagons are now 2-fold centers with mirrors passing through that. So the local site symmetry is 2 mm. So we can have either P2 mm or C2 symmetry. If you see, all of octagons now are identical. So if we look at a primitive unit cell, the smallest unit cell, that will be this rhombus. But we know that for P2 the primitive unit cell should be a rectangle. So here we will, although this primitive unit cell is possible, we will go for the conventional unit cell where the edges are taken parallel to the mirror planes. So we get a rectangle like this, and then the center point also is an equivalent lattice point. So the plane group is C2
That was quite a lot of symmetry to take in. Now I will carefully make my way down the stairs, keeping in mind how Emperor Humayun met his end. See you later. Bye bye.